Ceramic gray body is obtained through a different forming processes. The next step is sintering. Sintering is the most critical step for ceramic materials. So, what is sintering? In general, the goal of the sintering is to consolidate the grain body into a dense monolithic object. Sintering is also called firing. It's a process of compacting and forming a solid mass of material by heat or pressure without melting it to the point of the made ceramic particles. Here is a picture showing the change of the grain body to a ceramic after sintering. From a process point of view, a typical sintering profile is drawn here. Sometimes the function of the heating the gray bonder at low temperature to burn off the binder is not a real sintering. This is called pre-sintering or die bending stage. They can heat separately or continuously. Sintering are processing at a high temperature to fuse the ceramic particle together. The sintering profile typically includes a temperature ramp rate, final temperature, hold time, and sometimes a cool down ramp rate. Whenever for the traditional ceramic or for the advanced ceramic, the sintering processing is the key step. Why the sintering is the key step? Because at this stage, in a high temperature, physical and chemical changes take place inside the ceramic grain body. Ceramic powder in the grain body are lossy powder. In this state, the powder particles are just lightly joined together. The grain body has a so-called grain strength, which is usually only sufficient for handling purpose. It's the sintering processing that connects the dots strongly, making soft grain body hard, improves the strength largely, reducing the porosity, and increasing the density of ceramic. A sintering furnace or ovens is used during the sintering process. The basic function of a furnace is controlling the heating and cooling rates as needed, and having a uniform temperature filled inner chamber of the furnace. Different sintering furnaces can achieve different sintering atmosphere. Therefore, the diversity of sintering furnaces are necessary for the control of the sintering parameters. For most traditional ceramics, they are centered in an air atmosphere, such as ceramic tiles sintering we mentioned previously. We see that the sintering equipment is kiln, a continuous sintering furnace. Although sintering has been practiced for thousands of years, significant advances in understanding the phenomena have been made only in the last 6 decades. Let's take a visual look at the key microstructural changes during sintering process. Essentially, sintering is the extension of the contact area between powder. During sintering, a powder compact is heated at a temperature below the melting pot or range of the made powders, but high enough to bond the individual particles by diffusion of atoms. This diffusion is caused by a gradient of chemical potential. Atom moves from an area of higher chemical potential to an area of low chemical potential. The different paths the atoms take to get from one spot to another are the sintering mechanisms. There are 6 common mechanisms of sintering, such as surface diffusion, vapor transport, lattice diffusion from surface. The above 3 mechanisms are non-densifying. They take atoms from the surface and rearrange them onto another surface or part of the same surface. These mechanisms simply rearrange matter inside a porosity and don't cause pores to shrink. The other three mechanisms are lattice diffusion from grain boundary diffusion, and plastic deformation. The last three mechanisms are densifying mechanisms. Atoms are moved from the bulk to the surface of pores, thereby eliminating porosities and increasing the density of the sample. Here is a centering simulation in 3 dimensions. We see the diffusion occurring among multiple particles through centering, gradually forming a grain boundary surrounding the grains. At the same time, the amount of pore and their size and shape are changing. Also, the grain is growing and the bulk sample is shrinking. As a result, many evolutions finished and the total changes happened, and different stages of centering are summarized in this table. Give you a pause here. Please see the detail and have a second think. There are many factors affecting the property of the centering ceramics. The main is the property of the pounder, the forming conditions, and the centering conditions. The property of the pounder and the forming condition are decided in the previously step. The factor of centering condition including heating rate, centering temperature and time, cooling rate, and centering atmosphere and centering pressure, and so on. Centering temperature and time. The centering temperature and time influence the porosity, the density, the strength, and the hardness of the centered ceramics. When centering temperature is too high and time is too long, the performance will be degraded, or even there will be overburning flow. On the contrary, if the centering temperature is too low or time is too short, the performance will be degraded due to underburning. Let me give you an example of the effect of centering temperature on the chroma and translucency of zirconium ceramics. We can see the obvious difference is influenced by the change of the centering temperature. This type of zirconium ceramics is used as a dental material. Centering atmosphere also have a direct influence on the property of the centered product. We list several most used centering atmosphere. The selection of a centering atmosphere is most often decided by the choice of material, desired properties such as density, mass, shape, production demands, and product service condition. Different gases such as nitrogen, argon, hydrogen, or their mixture can be used for a certain purpose during centering. For example, centering in a reducing atmosphere can prevent the burning loss or reduction of the oxide in the processing. Vacuum centering is also an effective method for obtaining densely centered ceramics. It can avoid the adverse effects of harmful components such as oxygen, hydrogen in the atmosphere, and also reduce the centering temperature about 100 to 150 degrees Celsius. For the detail of the centering method, because there are so many different types of ceramics, so their related centering methods are different. We have known that the final centering temperature is a key factor influencing the quality of the centered ceramics. There are second or third external force such as pressure, electrical current also can be applied to affect the centering qualities. A commonly used secondary external force is pressure. So The sintering that is performed just to use temperature is generally called pressureless sintering. In other words, in order to improve the quality of the sintered ceramics, such as the density, the flex strength, and so on, many other sintering methods have been developed and applied well in their specific fields. The novel sintering method includes liquid phase sintering, reaction sintering, pressure sintering, flash sintering of ceramic, and microwave sintering, and so on. In our research group, many students are focused on the reaction-bound silicon carbide preparation and their applications. That is one kind of the reaction sintering. From this diagram, we can see the liquid silicon reacted with porous carbon perform, and the silicon carbide was formed at the temperature above the silicon's melting pot. The new reaction formed silicon carbide, and some unreacted silicon bound the particle during the cooling stage. As a result, a dense silicon carbide ceramic with high density, high strength, and very low porosity is obtained by this sintering method. Now we are seeing the microstructural change of the reaction-bonded silicon carbide material. Here we also see some reaction-bonded silicon carbide ceramic products. They are products of near-net shape of processing. In our lab, we have another novel sintering furnace, that is spark plasma sintering. There are two forces applied during the sintering except the temperature. One is the pressure, the other is the electric current. With those two external forces, the spark plasma sintering hitting the pounder very quickly and can lower the sintering temperature. In particular, it has been reported in a lot of research papers. Plasma discharge is occurring during the heating. That is called plasma heating, which enhances the heating rate. The SPS processing also features a high thermal efficiency because the direct heating of the sintering mold and the sintered materials. Therefore, this has made SPS processing a good method for preparation of ceramics based on nanoparticles, which enhance the magnetic or optical properties. SPS is also used for sintering of nanotubes. After sintering, the grain body becomes harder and have a relative high strength. Some of the ceramic parts can be used directly after sintering, but the other ceramic parts need to be further prepared before it used. Therefore, the ceramic parts used in high precision manufacturing often require adjustments to be made at the micro or nano scales. That means the fifth step, secondary processing, are very necessary. First, we see the processing of grading and polishing. This is an important process that is designed to fabricate products with high levels of dimensional accuracy and mirror finished surface. That means the surface is very smooth. Because the ceramics are extremely hard, it's necessary to use diamond, the hardest material in the world, for the grading and polishing process. The right photo shows several selection of ceramic medical parts. At least one surface of the part are polished. They have a very little fraction with human bodies. Bonding. Ceramics is brittle and not easy be machined, so they can bonding with metal to solve some difficult problems. This is an important and volume-ending process for drawing multiple ceramic parts or drawing ceramic products to metallic or resin materials. Actually, some artificial tools are the material bonded with metal and ceramics. Metallization. Metallization refers to the process of affixing a metallic layer to the surface of a centered body to form conductive patterns or provide hermetic sealing. One method involves coating the ceramic surface with a paste containing metallic powder and then apply high temperatures to burn this metallic layer into the surface of the ceramic. A related method involves applying metallic layers through an electroplating process. The final step is inspection of ceramics. Like other important products, ceramics parts have to pass a strict inspection before their application. Special attention should be paid to the mechanical integrity, geometry measurement, and other functional tests. This step is more a matter of quality control in actual industrial production. When the raw material of ceramics are determined and the correction preparation method is selected, the microstructure of the obtained ceramics will be formed. Then, what's the feature of their microstructures? We will explain it in our next video.